Showtime!
Ladies and gentlemen, please make your way to your seats.
Showtime!
Please make your way to your seats. The show is about to begin.
Showtime!
Let the magic begin.
Welcome back to Futuretech, your weekly source for the latest in tech and innovation. I'm the startup coach, and I'm joined by my co-host, John Irwin. How you doing today, John?
I'm good. Craig, how are you?
Good. And I just realized you were way over in the corner of my TV that I use as a monitor, so I'm looking way away from the.
I'm right beside you on mine, so yeah.
And people keep telling me you don't look like you're paying attention. That's because I keep moving the windows around because I got but I am paying attention.
It's I don't get it nowadays. Everyone has multiple monitors, so they should be used to people looking elsewhere, right? I don't know.
I guess when you're live in the webinar, people are. But I move the windows around because I got to share the screens. I got to do all the stuff, and that means I'm looking. For those people who are joining us, thanks for joining us. But I got a 43-inch TV behind me that in front of me that I'm using, so I'm going like this. It's
yeah, you do all of the back end work. I just show up and yap.
Well, I just show up and, for lack of a better word, I'm the straight person here. From you got all the details. I'm the regular person that's going to ask the questions. Yeah. I don't know if that's true or not, but we'll go with it.
Yeah, let's go with it.
All right, let me get rid of this and that. And so let's get into the first one here. Reverse microwave.
Yeah.
Super cool. And it actually works.
I think so.
So for cooling?
For cooling instead of heating. So, and don't think of it like microwave, because it's not microwave technology like what it is in an actual microwave. So the article itself, it discusses it's an innovative new solid state cooling technology, which was developed by researchers in Luxembourg. And it functions like, and they're calling it a reverse microwave because it's supposed to cool really fast to rapidly cool objects. So what it uses is an electrocaloric effect rather than vapor compression for cooling. So vapor compression is used in a whole bunch of different devices right now. It's not very eco-friendly. So this is going to be really interesting if they can commercialize it. So what the electrocaloric effect does is it causes certain materials like aluminum to heat up or cool down when an electric field is applied or removed. And so the researchers configured electrocaloric capacitors that alternate between heating and cooling cycles by switching the electric field on and off. Pretty straightforward. The cool thing is the electricity-free system can efficiently pump heat without needing bulky, greenhouse-emitting compressors that are required in refrigerators and air conditioners. So it actually represents a more sustainable and energy-efficient cooling method. And this is cool because I was doing I went down the rabbit hole about using magnets. Apparently you can use magnets to cool things. And I think I don't know how similar it is. And I didn't do a deep dive into the comparison, but the cool thing about the magnet thing is that, again, it doesn't use greenhouse gases. It doesn't use too much electricity. So this is really interesting. And so the way they did this is they pair the capacitors with liquid coolant to enable the rapid heat transfer. And then when an electric field is applied, the coolant heats up, which cools the system through the electrocaloric effect. And then reversing that process releases the heat buildup. So they envision applications in kitchens to quickly cool foods, consumer appliances, electronics cooling, industrial uses like semiconductor manufacturing, where heat management is critical. And so, yeah, it's really cool. It's promising, but more research is needed to optimize the materials and configurations for commercialization. But it does demonstrate how new physics breakthroughs can disrupt entrenched engineering paradigms, which is awesome because most of the things that we're using to date for cooling are just horrible for the environment, not efficient, just not sustainable at all.
So when I think the concept of a reverse microwave, are we talking about like cooling a plate of food, or are we talking about a freezer?
I That's a good question. I'm thinking I think you're going to be able to control it. So I'm thinking here, based on the technology here, if they can get it to a place, it's going to be either like rapid freezing or cooling to a point. So you put a beer in there and it'll cool within seconds, kind of thing. Or you want to freeze something, flash freeze something, you could probably use that too if they get the technology there. I don't think it's there yet. I think it's obviously still in more of the concept phase. But I think once they prove it and commercialize it, it won't be like a microwave where it's got this. The way a microwave works is if you're heating something up, it turns on and off as you're heating it up, right? So or it stays on, or depending on the power strength. Where this is, I feel like it's more of a blast of air, but I could be wrong. We'll have to see what they end up with.
Yeah, I'm looking at this and it looks very interesting, but I didn't have any links to follow up with this one, just to go down the rabbit hole like you had did. It looks very interesting. It's electricity free, and you kind of explained how it works. But you're talking about a vapor.
Well,
there's got to be. Go ahead.
Yeah. Let's dive into that. So, and it's let's get into the details of that. So, and it's called the electrocaloric effect. So, what it does is it causes certain materials like aluminum to heat up or cool down. So, different types of materials that they're going to have to experiment with. But the way it happens is it's due to the interactions between the electric field and the electric dipoles or ferroelectric behavior in the material itself. So, in a system like this, they use a capacitor, which is made of an electrocaloric material like aluminum as one plate. And then when an electric field is applied, the material heats up as its temperature increases. Now, on the other side of the capacitor is a liquid coolant. So as the material heats up, heat is transferred to the coolant, causing the coolant to get hotter while the material cools down. So by alternating the electric field on and off, the heat gets pumped from one side to the other in a cyclic kind of process. And then the hot coolant then passes through a heat exchanger to dissipate the heat. That's how it achieves kind of like a solid state cooling with no need for refrigerants or compressors like vapor compression systems. It's more efficient. There's less energy wasted. It's just the resistance losses in the material. So vapor compression systems, they lose energy through compressor work, pressure drops, and phase change losses. So they have having fewer moving parts in this and the direct electrocaloric heat pump, it hugely reduces systemic energy losses, if that makes sense.
Absolutely does. Just the question becomes is how energy efficient is this? It says it takes no electricity, but it sounds like eventually the system needs to be refueled with something.
Yeah. So if we're comparing it to traditional vapor systems, so a few things. There's fewer components and moving parts, as I just mentioned. There's no refrigerant phase changes. So avoiding liquid vapor refrigerant transitions, it improves efficiency. There's less temperature difference. So there's solid state heat pumping that works with smaller temperature gradients. There's better heat transfer and there's less pressure drop. So overall, based on what I was reading, this new design is estimated to achieve 2 to 5 times better energy efficiency compared to the vapor compression refrigerator. So I know that in the article they said what did they say? Electric free or something?
Yeah.
I don't think that's the case. If we're looking to commercialize this, obviously, because you're applying an electric field to this, right? So I don't know where they're coming from with that.
Yeah, because here, right at the end, it says The reverse microwave is something we've been asking for years, but this one also works without electricity and is 100% sustainable.
Yeah, I think that maybe they got GPT to write that because it doesn't align with the physics and everything that they're talking about in the article itself.
Yeah, so there's some questions here about this. It's interesting from as the world goes to a more sustainable place, and they talk about global warming, and whether we're actually headed in that direction or it's cyclical. We're heading into a warm cycle or a cool cycle because it's more, and we're more extremes as the world as we transfer. Because back in the 70s, it was global cooling.
Yeah.
Nonetheless, this kind of stuff could potentially reduce our electrical capacity, keep things, cool in a hot environment. I could see this applying in many, many ways. Do you see this kind of thing moving out of, say, the kitchen?
Yes, absolutely. So let's just start off with food and bev. So you could rapidly cool foods, you can accelerate food processing and chilling beverages, which we talked about. So medicine by cooling medical devices. You have controlled, like really good controlled temperature storage for drugs and vaccines. And I'm sure it's going to be a much smaller device than what you would need currently. So lab equipment cooling. So then we got electronics cooling smartphones. So if they can minimize this enough, potentially could cool smartphones, computers, high power laser diodes, so we can have more powerful lasers. Automotive, we could put this in. This could be our new air conditioning, right? Cooling seats, steering wheels, thermal management of batteries, and power electronics, which would be good for EVs if they still continue to take off. With aerospace, you could have lighter and more reliable cooling for avionics compared to vapor compression, which is what they use currently. The cool thing is, I'm guessing based on what I'm reading, is you can have a more precision temperature control. So this would be good for chemical and pharma when you need precision temperature control for chemical reactions, bioreactors, drug synthesis, and then residential air conditioning, refrigeration, so many things. Data centers, that would be a huge impact for data centers. So lots of potential use cases.
Definitely. So the question is, when I see this picture at the top and I think about microwave oven, I don't think about putting one of these on the wall to cool my house because I feel like I'm going to be fried. So, is it safe for,
Yes.
people?
So the thing is, and that's the problem with using, again, with using the word microwave, is it's not using microwaves, right? I guess they just use that word to kind of get people to understand, or get people to put it into an idea that they can understand. But this is safe. You're using electricity, and you're using capacitors, which is in every device that you have. You have capacitors in every device. You have capacitors all over the place. And if you think about it like this, you have an air conditioner most likely in your car. There's no protection around that. You have an air conditioner outside. There's no protection around that other than the metal encasing it. The thing is, the biggest difference is this doesn't use any frequencies, any radio frequencies, like how microwaves do. That's the biggest difference.
Yeah, and I just wanted to make that clear because it looked
Yeah.
like they didn't do any of that in the article. But then you see this picture of the person in the clean room and you wonder, well,
that could be a picture because, losing my voice from last night, too much talking and more talking today. But that could be him cooling a microchip or some sort of circuit board in a clean room is what it could be. But who knows?
yeah. It just could be B footage from a person in a clean room, have nothing to do with what we're talking
Or
about.
a generated GPT image.
Yeah, so we always have to keep all of those things in mind. I love this idea because, next to free cooling, because it's supposed to be no electricity. We'll have to see how that works.
Yeah.
this looks great. The question
does.
now becomes, how big? Like you talk about sticking something like this in air conditioning your car. Is it
Yeah.
small? Is it big? Is it?
I'm guessing it is because there's way less parts that are needed for this. In order to create an efficient cooling cycle system kind of thing. So I think right now in air conditioners, you have the compressor, you have the gas, you have a whole bunch of different parts that are in a car, that are in your air conditioner outside. The cooling coil, which people know, like the cooling coil, that always or doesn't always need to get replaced, but that's a part that you see replaced in movies and things like that. It's going to be much smaller. Now, what does it look like now? How big is it now? Who knows? But we all know that when you're developing new technology, new prototypes are always much bigger than what they most of the time end up being at the end of the day. So I'm going to be interested to see where they go with this, how long it takes to get to a prototype and then to commercialize it and see how big that size is for sure.
And are they going to have to use a different measurement for cooling? Like when we go and look at air conditioners, they talk about BTUs and stuff, so you get an idea of the size of room something cools down. But is that the same? Are we going to have the same efficiencies in one of these? Would it and be measured by BTUs, or would it be something else?
Who knows? So when I was reading this, there was something called the Carnot limit that I was reading about. Maybe they start looking at that. It's also known as the Carnot efficiency. It refers to the maximum possible efficiency that any heat engine can achieve when operating between two specific temperature reservoirs. So who knows? Maybe they start using that as a measurement on top of BTUs. I'm guessing because they referenced it in this article. I'm guessing they'll start. It'll have some sort of relevance as they develop.
All right, I got two final questions for you, unless the audience wants to ask us something. Timing and cost. When are we going to see it, and how expensive is it going to be?
No clue. Like you said, like I couldn't find too much more about this, but so here it is. Based on my expertise that I know of materials and the types of the design that they're doing and things, it doesn't seem like it's too far off because they're using essentially known technologies. Like they're using a capacitor design, they're using aluminum, they're using they're using parts and concepts that have already been proven, just putting them together and designing them into this new kind of design kind of thing. So I don't think, I know we always use the 5 to 10 year thing. As far as cost goes, no clue. But I'm guessing if they're talking about this being implemented into houses, into cars and things like that, it's got to be either the same or cheaper than current systems, right? So I know that's not a good answer, but yeah.
Yeah, obviously, it cheaper, more efficient. I don't know if it has to be cheaper, but more energy efficient because
Yeah.
we're living a brave new world where people will spend a lot more if my electricity bill is dropped by this technology.
For sure. But like it seems like it should be cheaper because they're not reinventing the wheel with any new materials. They're not reinventing the wheel with any kind of new designs. They're just kind of combining they're using concepts and combining in materials that are readily available. So, and they're using apparently less components in this too. So obviously new tech, there's going to be a premium because they did some R&D and things like that. But yeah.
Well, I mean, it'll be cheaper to produce and manufacture, but let's face it, what, we are living in a capitalistic society. Look what happened with EpiPens and stuff that used to be nothing, and now they're thousands of dollars, and it's what? Because people, they get a monopoly or patent, and they can charge what they can charge. So, and people are always trying to make a buck. So, we'll have to see, right? If this is putting the air conditioner business people out of business, or maybe it's not. Maybe they're a whole new profit center for them because they switch everything over.
Exactly. Yeah. There's this thing, and I should have dove into it before this, but there's these new things that I'm seeing advertising called heat pumps that are supposed to replace the air conditioners right now. And
Heat
I
pumps
should
been
have,
around for years.
yeah, but I should have. I haven't even looked at that technology, and I should have for this. But yeah,
Yeah, they're okay, but
yeah,
they're more energy efficient. They're not as good as air conditioners.
yeah.
But they do both heating and air conditioning.
Okay, cool.
Yeah.
Interesting.
All right. Any final words before we move on to the next thing?
No, just this isn't microwave technology. It's just a type of way of cooling. Just so those, for those that are worried. And by the way, for microwaves, for those that don't know, those black dots on the door of your microwave, they're there to keep the microwaves inside, and so that your face doesn't fry when you're looking at your food cooking. By the way, for those little fun, useless fact Thursday.
We know that you work with tech companies to help them get government funding and navigate the fun world of being a startup here in Canada. Anything you want to add to that, and where can people go find out more if they have questions about, funding and want to talk to you?
Yeah, thanks. Yeah, send me a message on LinkedIn. Find me on LinkedIn. Very easy. John Irwin, no H. And I'm happy to have a discussion. Happy Craig and I work very closely together. So if there's something that I feel Craig might work better with you on, I'll definitely pass them your way. But if you have any questions on non-dilutive government funding, hiring grants, training grants, shred any tax credits or any kind of grants, feel free to reach out to me.
And if any of you listening, the audio or video is breaking up, we do separate local recordings. It takes a while to come out, but the audio will be pushed out on the podcast. We push it out. We're about 2 weeks behind when the podcasts come out. We're just from the timeline point of view, but we'll get great audio and stuff there. Check out all of our stuff. We help entrepreneurs. We do events. We were just talking about last night. We were at Startup Drinks TO. We were at CIX after party. We had 100 people out. There was about 20 investors in the room. It was a great time. It's open pitch, open bar. Check out startupdrinksto.com. The next one will be April 25th, and that'll be posted by the time you're seeing this. I work with startups all the time. If you're stuck in your business and you don't know where to go and you want to move forward and you're frustrated, book a discovery call. Go to startupcoach.ca. It's absolutely free. We can chat about how I can help you and how to get unstuck and actually turn your business into a profitable, successful, and a happy place for you to work. Check out our stuff at TorontoStarts.com. Thanks for watching us today.